welcome back students. So in this video we'll be doing question number 4. Okay, this is the question which is given. Okay? We're asked to show that the square of any positive integer, alright, is either of the form 3m or m plus 1 for some integer of m. Okay, so let us first try to understand what. Remember, m must be an integer, so I hope you already know what an integer is. Okay, and we're asked to show that. Okay, so let me just show. So let a be any positive integer. Okay, positive integer. Okay, all right. Now, and what is b given to us over here? It's quite easy to find out that b is 3. So by Euclid's lemma, we know that a is equal to bq plus r, where remainder is going to be a value less than b, or it's going to be a value greater or equal to 0. So a is going to be equal to 3q plus r, and you can write this as equation number 1. Okay, so and your r is going to be a value less than 3, and it's going to be a value greater or equal to 0. This is what we know. Okay, what is given to us. All right, now we're asked to show that the square of any positive integer. So the square, that means if we take this is a is a positive integer, the square of this positive integer is 3a squared. We're asked to show that a square is either of the form 3m or 3m plus 1. Okay, this much we know. Okay, so let us go now. So the possible values of r. Okay, and remember, r is going to be a remainder. R is going to be a value less than 3, greater or equal to 0. So 0, 1 and 2. Okay, this much we know, right? Remember. Okay, so let's see, when r is equal to 0, what do we get? In equation 1. So when r is 0, we get this as 3q plus 0, which is 3q. A is equal to 3q, but we are asked to show that the square of any positive integer, right? So we have to take the square of this. Okay, and if you take the square of this, you have to take square on both the sides, so you'll be getting this. Okay, so after this, you just come over here, you get this as a square into 9q square. But what I'll do is I'll just remove them. Okay, just give me a second. We'll write this as 3q into 3q. So right now what we need here is we need to find out in the form of 3m or 3m plus 1. So you write a 3 over here. So if you take 3, what remains is 3q square, right? I hope you're okay with this. Okay, so this is what we get. So I'm going to write, I'll write this as 3 as let's just call this k. Okay, where you can, in bracket you can write k as equal to 3q square. Okay, I'm just replacing 3q square with a k. All right, clear with this? Okay, we'll be coming back to that. Okay, now when r is equal to 1 in a, in equation 1. So in equation 1, our a was 3q plus r, 3q plus r. So this is going to be 3q plus 1. Okay, now you take squaring both sides, because we're asked to find out the square. Okay, squaring both sides, we get this as a square equal to 3q plus 1 the whole thing square. So take out the square. A square equal to, this is going to be of the form a plus b the whole thing square. So this is going to be a square plus b square plus 2ab. Okay, so 2ab, right? So you get this as a square. This is going to give you 9q square plus 1 plus 6q. Now what I'll take here is I'll write 9q square. I'll rearrange them, and then can I take 3 over here? If I take 3 common, I'll be left with 3q square plus 2q plus 1. Okay, so now I'll write this as 3. Earlier we wrote that as, so I'll write this as, you write this as k1. Okay, I'll just write here k1, and this is going to be k2 plus 1, and in bracket you can always write k2 is actually equal to 3q square plus 2q. Okay, now finally when r is equal to 2, what do we get? Okay, in equation 1, so when you put a equal to 3q plus 2 and you take the square, again you square both sides, when you square both sides you'll be getting this as a square equal to 3q plus 2 the whole thing square, so this becomes a square. So open up the bracket again, so a square plus b square plus 2ab, so 3q and 2ab. Alright, so this becomes 3q square is 9q square, this becomes 4, and this becomes 2 into 6, 6 into 12, 12q. Now what I can redo is, can I write this as 9q square plus 12q square plus, instead of 4, I'll write it as 3 plus 1, okay? So this way, you can take 3 common for these 3 terms, right? So if you take 3 out, you'll be left with a 3q square here. You'll be left, if you take 3 out, you'll be left with 4q, and you'll be left with 1. And you're finally left with 1, okay, plus 1. I'm taking 3 common only for this term, alright, because all 9, 12q and 3 are all multiples of 3. So a2, I can finally replace this as k3 plus 1, where you can write k3 is equal to 3q square plus 4q plus 1, okay. Therefore, alright, okay. Therefore, when r is equal to 0, our a was equal to 3k1. When r is equal to 1, a was equal to 3k2 plus 1. When r is equal to 2, what was our a? A was equal to 3k3 plus 1, okay. Where you see where k1, k2 and k3 are all integers, okay. Hence we have shown, okay. You can always conclude we have shown that, and you can write the rest. We can show that the squares of the positive integers is always going to be in the form 3m plus 1, 3m plus 2, okay. But before that, you write the conclusion, okay. You write what is given here. We have shown that the square of any positive integers is either of this form 3m or 3m plus 1. Alright, you can do that. Alright, see, there's absolutely no need to worry. There, you may be thinking, some of you may be thinking, it's written here m and then this is written as k1. It's completely different. No, it's not, okay. Remember what is given here. M is any integer. Is some integer. It's an integer. And what do we also know? K1, K2, K3 are also going to be an integer, right? So it's absolutely okay even if you replace your m with k1. Does not really make any difference. And k1, k2 and k3 are integers because you look at this. What is k2? First, let's focus with k2 is 3q square plus 2q, right? And you must understand, by division algorithm, q is always going to be an integer. Alright, all this you see, a, b, q and r, everything that you see for Euclid's division lemma, these are all going to be integers, okay. So even in the case of this, q is also going to be any integer, this is also going to be in any integer, right? So when you substitute q, you can take it as 0, 1, 2, 3, 4, minus 1, minus 2, you substitute, your k2 will be another integer. The same case for k3. You replace your q with any values that you want, okay? q1, q2, q3, q as 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 10, minus 100, minus 1000 if you want. And when you substitute that, your k3 will be another integer, clear? So that's the reason why I've written k1, k2 and k3 are all integers, okay? So we have to prove this given statement, and we only show it up to r equal to 0, r equal to 1, r equal to 2, because Euclid's division tells us that the value of r should be less than 3 and it must be greater or equal to 0. And remember, r again, it must be an integer only, okay? It must be an integer only, do not forget that, okay? So some of you might be thinking, why not 2.9? But this cannot be, because 2.9 is not an integer, alright? Okay, so we shall end the video over here.